Lithium-ion battery separators and materials. Lithium-ion batteries, LIBs, have emerged as a dominant energy storage technology due to the increasing global demand for environmentally sustainable and efficient energy systems. Their widespread use spans portable electronics, electric vehicles, EVs, aerospace systems, and grid-scale energy storage. LIBs are favored for their high energy density, long cycle life, broad operating temperature range, and high operating voltage. As the transition toward low-carbon energy systems accelerates, LIBs play a critical role in enabling renewable energy integration and electrification. A typical LIB consists of four essential components: a cathode, positive electrode, an anode, negative electrode, an electrolyte, and a separator. Among these, the separator is a crucial yet often underappreciated component. It is a porous membrane positioned between the electrodes, designed to prevent electrical short circuits while allowing ionic transport. The separator's structural and chemical properties strongly influence battery performance, safety, and durability. Consequently, extensive research has focused on improving separator materials and design to meet increasing performance and safety requirements. Function and importance of separators in LIBs. The separator performs multiple essential functions. Electrical insulation: it prevents direct physical contact and electron transfer between the cathode and anode, thereby avoiding internal short circuits. Ion transport medium: its porous structure allows lithium ions, Li+, to migrate between electrodes during charge and discharge cycles. Safety mechanism: many separators exhibit a thermal shutdown function, where pores close at elevated temperatures, interrupting ion flow and preventing thermal runaway. The design and material selection of separators involve complex trade-offs among mechanical strength, porosity, thermal stability, and electrochemical compatibility. Although separators are electrically insulating, their physical structure, particularly porosity, pore size, and wettability, directly impacts ionic conductivity and internal resistance. Therefore, separator design must balance mechanical integrity with electrochemical performance. Lithium-ion battery separator materials. Conventional polymeric materials. Most commercial separators are fabricated from polymeric materials due to their processability, cost-effectiveness, and chemical stability. Common materials include polyethylene, PE, polypropylene, PP, poly, tetrafluoroethylene, PTFE, poly, vinylidene fluoride, PVDF, polyacrylonitrile, PAN, polyamide, PI, poly, methyl metaacrylate, PMMA, poly, ethylene oxide, PEO, poly, ethylene terephthalate, PET, and cellulose-based materials. Among these, polyolefins, P and PP, dominate the commercial market due to their excellent mechanical strength, chemical stability, and thermal shutdown capability. In particular, ultra-high molecular weight polyethylene, UHMWPE, is widely used in automotive batteries due to its high safety performance. At elevated temperatures, UHMWPE transitions into a gel-like state without losing structural integrity, preventing membrane collapse. Preparation methods. Polyolefin separators are typically produced by dry process. Melt extrusion stretching produces highly oriented structures with good mechanical strength. The resulting structure has slit-like pores aligned in the machine direction. Wet process, thermally induced phase separation, TIPS, enables better control over pore structure and porosity. Despite their advantages, polyolefin separators exhibit limitations such as poor electrolyte wettability and significant thermal shrinkage, restricting their use in high-performance applications. Advanced separator materials and modifications. To overcome the limitations of conventional separators, advanced materials and composite structures have been developed. Inorganic coated separators. Inorganic coatings involve depositing ceramic particles onto polymer membranes. Ceramic coatings are widely applied to polyolefin separators to enhance performance. Common materials include aluminum oxide, silicon dioxide, titanium dioxide, zirconium dioxide. These coatings enhance thermal stability, mechanical strength, resistance to thermal shrinkage, safety under high heat conditions. For example, aluminium oxide-coated separators exhibit improved cycling stability and can withstand temperatures up to 200 degrees Celsius. A typical modern separator consists of a wet process PE base film with a ceramic coating, especially for automotive batteries. Organic coated separators. Organic coatings use polymers such as PVDF, PAN, PMMA, and polydopamine. These improve electrolyte wettability, adhesion properties, ionic conductivity. Organic coatings reduce the contact angle between the separator and electrolyte, facilitating ion transport and enhancing battery efficiency. Composite separators. Hybrid separators combining inorganic and organic materials provide synergistic benefits, including improved safety, mechanical robustness, and electrochemical performance. PP, PE, PP, shutdown sandwich. A widely used advanced separator design is the tri-layer PP, PE, PP structure, which integrates safety and mechanical performance. P core layer melts at approximately 135 degrees Celsius, closing pores and stopping ion flow, shutdown function. PP outer layers maintain structural integrity due to higher melting point. This design ensures both reliable thermal shutdown, mechanical stability under stress, and such separators are particularly important in high-energy cylindrical and prismatic cells. A typical modern separator consists of a wet process PE base film with a ceramic coating, especially for automotive batteries. Alternative separator materials. Non-woven separators, PET-based. Non-woven separators made from polyethylene terephthalate, PET, fibers are produced via wet-laid processes. Variants include ceramic-filled PET, CF, PET, ceramic-coated PET, CC, PET. Advantages: high thermal stability. Improved resistance to thermal runaway propagation. Limitations: brittle fiber structure. Lower mechanical cohesion without reinforcement. Aramid-based separators. Aramid fibers, e.g., Kevlar-like materials, offer exceptional mechanical strength. High thermal stability, greater than 400 to 500 degrees Celsius, resistance to shrinkage. However, dense packing reduces porosity. Ionic conductivity may be limited. Composite separators, ANF, MMT systems. Recent research focuses on aramid nanofiber, ANF, clay composites, such as those incorporating montmorillonite, MMT. Key features: ANFs provide mechanical reinforcement. MMT enhances porosity and ionic conductivity. Negative charge of MMT promotes uniform Li distribution. Benefits: suppression of dendrite formation, improved cycle life, e.g., greater than 90% capacity retention after hundreds of cycles, enhanced safety, delayed ignition under thermal abuse. Polymer electrolyte-based separators. Polymer electrolytes, PEs, function both as separators and ion-conducting media. Compared to liquid electrolytes, they offer lower flammability, higher flexibility, better safety. They are particularly suitable for next-generation flexible and wearable electronics. A typical modern separator consists of a wet process PE base film with a ceramic coating, especially for automotive batteries. Key requirements of LIB separators. Mechanical strength and dendrite resistance. Separators must resist penetration by lithium dendrites, needle-like structures formed during repeated cycling. Adequate tensile strength is greater than or equal to 20 megapascals, and puncture resistance are essential. Thickness typically ranges from 16 to 25 micrometers, although thicker separators, approximately 40 micrometers, are used in EVs for enhanced safety. Thermal stability and shutdown capability. Separators must maintain structural integrity between -20 degrees Celsius and 90 degrees Celsius. Thermal shutdown is achieved using materials with different melting temperatures. For example, PE-PP separators shut down at approximately 130 degrees Celsius while maintaining structure up to approximately 165 degrees Celsius. Ionic permeability. Efficient ion transport requires high porosity, typically is less than or equal to 50%, uniform pore size, less than 1 micrometer, low tortuosity. Permeability is measured using the Gurley value, where lower values indicate better ion transport. Chemical stability. Separators must resist degradation in highly reactive electrochemical environments. Polyolefins are preferred due to their resistance to organic solvents. Incorporating ceramic nanoparticles further enhances stability. Electrolyte wettability. Good wettability ensures efficient electrolyte absorption and ion transport. Surface modification techniques include functional group grafting, e.g., hydroxyl, carboxyl, plasma treatment, polymer coating. Lower contact angles indicate better wettability. Cost and sustainability. Reducing separator thickness lowers material costs. Additionally, the development of recyclable and environmentally friendly materials supports the transition toward a circular economy. Physical and chemical properties of separator membranes. Thickness. Optimal thickness, approximately 25 micrometers, balances mechanical strength and low internal resistance. Excessive thickness reduces performance, while insufficient thickness compromises safety. Tensile strength. Separators must withstand mechanical stress during assembly and operation. Biaxial stretching improves uniform strength in multiple directions. Puncture resistance. High puncture resistance prevents damage during manufacturing and operation. Standard values exceed 300 grams mil. Porosity and pore size. Typical porosity is approximately 40%, with pore sizes ranging from 0.03 to 0.12 micrometers. Uniform pore distribution ensures consistent ion transport and prevents uneven current density. Electrolyte absorption. High absorption and retention improve ionic conductivity and battery efficiency. However, excessive absorption may weaken mechanical strength. Dimensional stability. Separators must resist shrinkage, less than 5% at 90 degrees Celsius, to prevent electrode and short circuits. Air permeability. Measured by the Gurley value, air permeability correlates with internal resistance and ion transport efficiency. Electrochemical performance. Key parameters include ionic conductivity, 10–10 mS cm, cycling stability, rate capability. Electrochemical impedance spectroscopy, EIS, is commonly used for characterization. Material trade-offs in separator design. Separator engineering requires balancing several competing factors. Thickness versus mechanical strength. Separators must achieve minimal thickness while maintaining sufficient tensile and puncture strength. Porosity versus shutdown performance. High porosity enhances electrolyte uptake, ionic conductivity, and power capability. However, excessive porosity weakens structural integrity. It may compromise reliable thermal shutdown. Uniform pore size, shape, and distribution are essential for homogeneous ion flux and consistent electrochemical performance. Wettability and electrolyte compatibility. The separator must exhibit a strong affinity toward liquid electrolytes to prevent dry regions, reduce interfacial resistance, ensure uniform ion transport. Poor wettability leads to localized current density, promoting dendrite formation and capacity loss. Dimensional and chemical stability. Separators must remain stable under thermal fluctuations during fast charging, chemically aggressive environments, reducing anode and oxidizing cathode. They should also resist shrinkage, distortion, and oxidative or reductive degradation. Challenges and future perspectives. Despite significant advancements, several challenges remain. Enhancing thermal stability without sacrificing porosity, preventing dendrite penetration, improving electrolyte compatibility, developing sustainable and recyclable materials. Future research focuses on nanostructured and composite separators, solid-state and gel polymer electrolytes, functional coatings with multifunctional properties, eco-friendly materials such as bio-based polymers. Conclusion. Separators are indispensable components of lithium-ion batteries, serving as both physical barriers and functional materials that regulate ion transport and ensure safety. Their design involves balancing competing requirements such as mechanical strength, porosity, thermal stability, and electrochemical compatibility. Conventional polyolefin separators, produced via dry or wet processes, remain the industry standard. However, their limitations, particularly in thermal stability and wettability, have driven the development of advanced materials, including ceramic-coated membranes, composite multilayer structures, and non-woven systems. Recent innovations, such as aramid-based composites, clay-enhanced separators, and thermally responsive coatings, demonstrate significant improvements in safety, performance, and durability. These functional separators play a crucial role in mitigating risks such as thermal runaway and internal short circuits. As battery technologies continue to evolve toward higher energy densities and faster charging capabilities, the development of advanced separator materials will remain central to achieving safe, reliable, and high-performance energy storage systems.